Hello, Chem 1B. This is chapter 22, lecture video 5, and we're going to be talking about stereoisomers. Stereoisomers can be broken down into two groups: geometric ligands. Geometric isomers are where we have ligands that have different spatial arrangements around the metal ion. Cis versus trans, and Feisch versus Mer are our two types of geometric isomers. Now, cis versus trans can happen when our shapes are either square planar or octahedral. You can't have cis versus trans. You can't have cis-trans isomerism in tetrahedrals. You can't have it in linear substances. It's only ever going to be possible if your structure is a square planar or octahedral. Now, I like to try to remember these. I have like an analogy. I don't know it's right because I'm an only child, but I always like to think that cis reminds me of sisters, and sisters are close together. Like, they're friends. They're close. I don't know if that's definitely not always true, I'm sure, but we're going to pretend it's always true. And so these CLs here, you can kind of see they're right next to each other in this complex. So that's the cis isomer because they're right next to each other. They're sisters. They're close. The same thing is true of the ammonia. The ammonias here, the amine ligands, are right next to each other. They're cis to one another. Trans reminds me of transversing something, and transversing means across from something, right? So notice here the NH3s are across from each other. They're far away. That means they're trans to each other. The same thing is true of our CLs, right? They're far away from each other. This is the trans isomer. So I hope that helps a little bit. That's how I remember it at the very least. The Feisch versus Mer geometric isomers that we can have for coordination compounds only can occur when we have an octahedral. So if you have a Feisch versus Mer isomer, then then you're dealing with an octahedral. They can only happen in octahedrals. Now, with Feisch versus Mer, if we look at this picture, this is the Feisch isomer. The B's are purple. You can kind of see the purple atoms here, right? And if you look at them, they are all occupying one face of the octahedral. We call octahedrals because they have 8 sides to them. And in the Feisch isomer, 3 of one ligand are all occupying one side of the octahedral, or one face of the octahedral. You have to have 3 things that are the same ligand present in your octahedral, so like 3 B's here, in order to have Feisch versus Mer isomerism. So you have to have 3 of the same ligand in your octahedral to have Feisch versus Mer. Mer occurs when, again, I'm going to use the blue on the picture here. We have our purple atoms here, and if you notice, they're all on one plane of the octahedral. I like to think of this looking like a mohawk. Back in my punk rock days when I was in a band, I had a mohawk, 8 years ago. Oh, that's disgusting. Anyways, it's been that long. So this is how I remember it. You have them all in kind of the same line here on the structure. And that's the Mer configuration. Again, you need 3 of the same ligand to have Feisch versus Mer. All right, so we'll move on to the next type. Let's move on. Stereoisomers can also be broken into 2 groups, right? So the other group of stereoisomers are known as optical isomers. Optical isomers are where we have 2 compounds that are non-superimposable mirror images of each other. Think about hands. We got like our thumb, and then we got our fingers. Right, if I have two hands next to each other, my left hand and my right hand, and this is my mirror plane, then my other hand's going to be like this, right? So I got my thumb, there is no way these two images can superimpose perfectly because your top of your hand is different from the bottom of your hand. You can't make these lie flat on top of each other. There's no way to do it. Another example, more chemically appropriate, is these two. These two are non-superimposable. And in this type of scenario, it's really, really important to focus on your dashes and your wedges. No matter how I rotate these two molecules, they will never lie flat on each other, right? And so you're like, oh wait, but if I just rotate this over here, if I do like a 180 rotation here, have this guy go there, this guy go here, they should lie flat because the CLs will lie on top of each other and the I's will lie on top of each other. But that's not actually quite true. Let's do that rotation and see what I mean. So let's say I want to rotate this guy 180 degrees. So this guy's going to go here, this guy's going to go there, and vice versa. Right? And what I'm going to get over here is I'm going to get CL, PT, with dash, 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 CL here, and then wedge, I, and then I down here, and then wedge, NH3, and then dash, 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 NH3. Notice that the NH3s will lie on top of each other, but these two are flip-flopped here. They won't match up. There's no way to do it. By the way, this structure is also cis for Cl, and you can tell that because the Cl are next to each other at a right angle. If they were to 180 degrees, and cis for I too, actually. So that's just another thing that you can kind of say as a geometric isomer. But these are optical isomers because they do not fit on each other ever. They're mirror images of one another, in other words. No rotations will allow them to superimpose on one another. All right, so let's draw some isomers. Let's say we have a complex ion that is nickel, CN2Br2. Right, and it has a -2 charge on it, right? So there's actually two different isomers I can draw here. I can draw nickel in the center. We're also going to say that I told you this is a square planar. It's hard to tell if you have four things around your metal, like we do here. We have four ligands. Then your structure is either tetrahedral or square planar. Tetrahedrals don't have isomers, square planars do. So we're going to assume this is square planar for the sake of this problem, and it probably actually is in reality. I don't expect you to know how to determine the difference. I would tell you. So we have our square planar structure, and I'm going to just throw some stuff on here. This is the cis isomer, because as you can see, our BRs are next to each other and our CNs are next to each other. So this is the cis isomer for this structure. We could also have a trans. Here is the trans isomer. Again, they're across from each other with trans, right? And they're next to each other for cis. All right. So let's look at a little bit more of a complicated one. So let's say our ligand or our complex, coordination complex is CO NH3, 3, Br2, and Cl. and we'll say it at a 3+ charge on that. So this is actually a neutral compound. All right. So we're going to start. There are actually a number of different ligands we could draw here for this guy. So cobalt's our center. It's an octahedral. I know that because I have 3, 5, 6 things attached to it. So I'm just going to start by putting NH3 up here. And I'll use my dashes and wedges. NH3 there. And let's say I do Br here. And oops, an NH3 here. And Br here. And then we have our Cl down here. So this is a mer trans compound. You can see that it is mer for the NH3s, right? You can kind of see that plane, right? There, 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 right? But it's trans for the BRs. Hence the mer trans name. We could have also drawn this as mer cis, right? So let's do that, right? So I'm going to just edit this structure. So instead of mer trans, we could have had it as mer cis if you just change the location of these two. So Br comes here, Cl there. Notice now these two are next to each other. So this is mer cis for Br. Mer NH3 cis Br. We can draw it as Faish as well. Let's just do NH3 here. NH3 here, and then Br. This is Faish, again for NH3, and cis for Br. It is not going to be possible to do Faish trans because these three take up the spots that you'd need it to be to have a trans structure. So this is the only Faish conformer we can actually have. All right, so there's one last thing I kind of want to talk about here, and that is how do we tell, a structure is an octahedral or a square planar or a tetrahedral? Well, the square planar tetrahedral thing, I'll tell you that. But you need to be able to look at ligands and go, oh, these guys add up to 3 coordinations or 4 coordinations or 6 coordinations, telling you what the shape is. Now, in order to do that, you need to know what ligands are bidentate. And I will only use 2 ligands that are bidentate, and that is oxalate, C2O42-, and ethylene diamine. These two, oxalato, I guess, these 2 ligands you should know as bidentate. So if I have 2 ethylene diamines in my compound, they're taking up 4 spaces. So if I just have 2 ethylene diamines, then I have a square planar most likely. Or if I just have 2 oxalates, that means I'm taking up 4 spots around my metal center. If I have 3 of either of these, then that's 6 spots. That's an octahedral just with 3 things by itself. So you should know that about these 2 ligands. All right, so as always, if you have any questions, please feel free to email me or come to our Zoom meetings.